Buongiorno. Bonjour to everyone. Good morning, everybody. So it's a great pleasure to have for our final IP colloquium speaker of the year, a visitor who's come from California just to present our colloquium today and yesterday's ICAP seminar. It's a great pleasure to welcome Stefano Profumo from California, Santa Cruz, where he is professor of physics and director of graduate studies, and has been there since 2007. Okay, so before then he got his PhD in Italy at the at CISA, and then spent postdoctoral periods in Florida and at Caltech before getting his academic appointment. So Stefano is one of the world's leading experts in the field of astroparticle physics, and his interests span the entire range of model building, high energy astrophysics, and theoretical antiphysics that goes into our understanding of these elusive particles that are our best candidates for the dark matter in the universe. Great pleasure. Stefano is going to talk to us today about black holes as dark matter.
Thank you very much for having me this morning, and good morning, you all. You all live in a fantastic, amazing place. And as a European, I've been brainwashed by living in the United States for 20 years. But there is an inner vibrational mode that gets very excited when I visit a place like Paris. So thanks for having me. I have to say that the place where I live and work is, as you say, pas mal. This is my campus at the University of California, Santa Cruz on the Monterey Bay. I will be here until this afternoon, and I do look forward to meeting personally and scientifically as many of you as possible. So please come see me or contact me at my email. And if you are ever in California, please do reach out to me because I'd be delighted to host you. Today I will talk about many things, but I will not talk in depth about everything that I would mention. So if you're curious about a certain topic that I mentioned during my talk and you'd like to go further in depth on that topic, please again, ask me maybe later and reach out to me in any case. There is very compelling evidence that in the universe, galaxies like our own are embedded in large halos of dark matter. In fact, there's evidence that in the universe at large, 5/6 of what we call matter, which in general relativity we call a non-relativistic matter component, is something essentially fundamentally different from the matter that we know and love. In fact, there is compelling evidence that this dark matter is a new elementary particle, is a new constituent, is a new field that is not included in the standard model of physics. So it is worth asking, what is an elementary particle? Imagine that you go on a date and your date asks you, well, what do you do for a living? And you say, I study elementary particles. And there's one way in which that date is slated to become a complete disaster, which is if you tell the truth, as often is the case. And the truth is that an elementary particle is an irreducible unitary representation of the Poincare group. Right, so go with that with your date and see what happens. Now, this is a mouthful, but it does contain quite a bit of information thanks to his jolly Hungarian, Eugen Wigner, that produced a very important theorem in field theory, the Wigner representation theory, that tells us that every unitary reducible representation is labeled by two quantities. an integer or half integer quantity called the spin of the particle, and a real number that represents the mass of its particle. And this tells you completely what this particle does under transformations that belong to the quantum category. Now, I've mentioned that the dark matter is a new elementary particle. So it makes sense, in view of the work of Wigner, to ask, what do we know about these two quantities when it comes to this new elementary particle? The first thing we know is that quantum effects related to the existence of this particle should not get in the way of what the dark matter must do cosmologically, which is to form halos that trigger the formation of stars and eventually the formation of galaxies in the way that we observe in the universe. So what does this mean? Well, it means that the quantum pressure related to the fact that a particle behaves quantum mechanically as a wave and therefore has an intrinsic quantum pressure, this quantum pressure should not get in the way of the formation of the smallest structures that we observe being embedded in dark matter halos. These structures are dwarf galaxies, right? There's many around our own galaxy, the Milky Way. And so if you quantitatively want to attach numbers to this statement, you want the de Broglie wavelength of the particle, so h divided by mv, be smaller than the size of these dwarf galaxies, right? We know v because these galaxies belong to a halo of a given mass, and therefore the virial theorem tells us what the velocity dispersion of a typical particle in a dwarf galaxy is. And, you know, if you're a theorist against your instincts, putting numbers, what that amounts to is there any way, Florent, to get rid of this?
Probably it's actually on your laptop.
It is not on my laptop, actually. As Florent works on this, if you put, again, numbers in this equation, what you find is that there is an absolute lower limit, right? Because the de Broglie wavelength depends inversely on the mass. There's a lower limit on the mass of any dark matter particle, which is on the order of, thank you, Florent, of 10 to the negative 22 electron volts. And that's a very, very small number. Right? It's a very, very small number. It's 28 orders of magnitude smaller than the mass of an electron, right? In particular, this means that if you want to stack so many particles in a dwarf galaxy, you'd better have bosons. So you'd better have an integer spin for these particles. In fact, if you put in fermions, Pauli's exclusion principle actually moves this limit to much higher numbers, around the kilo electron volts or so, so 25 orders of magnitude north of this point. Now, what happens in the opposite regime when the dark matter as a point object is very massive? Well, what happens is that, as you imagine the dark matter being a very heavy thing that plows through objects like this is a cluster of stars, a stellar cluster, globular cluster, or objects like this, these galaxies, which are observed to be very stable, right? If you imagine that this galaxy lives in a dark matter halo populated of large point particles, you can easily imagine that this disk would get warped by the passage of the particles and the tidal interactions that passage would cause. Now, if you put in the numbers, what you get is that the mass of these very heavy dark matter particles must be less than a few solar masses. Again, you put in the numbers against your instincts if you're a theorist, and you find that this is 10 to the 67 electrons. If you're curious about the state-of-the-art calculation of these limits, I recommend that you look at this paper that just came out. We carry out this exercise in great detail and for the first time in actually detailed numerical simulation type approach, as opposed to what was done in the past, which was semi-analytic. And so if you want to know more about this, please do ask me. I'll leave it at there. So let's go back to Wigner. Let's go back to mass and spin particles. We have on the one hand, macroscopic quantum effects. On the other hand, these tidal disruption effects. This leaves us with a huge landscape of possibilities. In fact, over 90 orders of magnitude. So that's staggering. That's very depressing, right? Because that is immediately a landscape. And across this landscape, we've had a love story. We've had a love affair with one particular corner for very good reasons. And folks like Marco and myself spent a good part of our career thinking about candidates that populate the electroweak scale. And of course, I can tell you why. There's stuff called the weak miracle. There's the notion that the only interaction that could bridge between our visible sector and the dark sector is probably weak interactions. There's many reasons, right? There's good reasons. However, is there a good enough reason to spend all of this emotional energy and all of this financial energy, millions and millions of dollars, to explore this parameter space, which, put in perspective, is very, very narrow. Now, the love affair I showed is actually constrained to just a few orders of magnitude around the electron scale. But perhaps not. Perhaps it's worth thinking about a broader landscape. And before I go there, let me introduce another jolly character, Max Planck. Planck pointed out that gravity has a fundamental mass scale associated to it. By natural units, this mass scale is related to Newton's gravitational constant. And this mass scale is important because the Planck scale is the mass scale at which the Schwarzschild radius corresponding to a mass m equals the Compton wavelength of that mass. It is Schwarzschild radius, so the size of a black hole corresponding to that mass equals the Compton wavelength of that mass. As you grow the mass, the Compton wavelength shrinks, and what dominates the nature of that particle is its general relativistic behavior, right? So north of the Planck scale, it really does not make sense to talk about an elementary particle. What you should talk about, if you think about the most fundamental, the smallest possible constituent, is a black hole of a given mass. So interestingly, as you may very well know, black holes are also objects that are very simple, and they're fundamentally classified also in terms of very few parameters. In fact, essentially 3 parameters. If we don't think about the charge, black holes are classified also by their mass and their angular momentum. Of course, the angular momentum is, in this case, not quantized, because we don't know what gravity does when you put it together with quantum mechanics. But this is quite interesting. And so in my talk today, I will be looking at this vast landscape of masses where we are not talking about elementary particles, in fact, but we are talking about essentially what at a fundamental level we would call black holes. This landscape is big, is very big, and it ranges from candidates that Joe and myself are quite keen on, that live at a Planck scale, all the way up to candidates that hit that limit, that upper limit that I was talking about, just roughly stellar mass objects. And in between, I will take you on a journey. Hopefully that stays up there. On a journey that will start with stellar mass. Now I doubt it. With stellar mass black holes. My God, I'm probably gonna talk from here. I will then talk about asteroid mass black holes. This range is very interesting for reasons that will become clear. This is the range where there's now conclusive evidence. And if there's one thing that you bring home from this talk, let it be this fact. This asteroid mass range is the range. Oh, it's behind me. Okay, that's even more intimidating. Where black holes can be 100% of the dark matter, 100% of the dark matter. They can be all of the dark matter if they weigh as much as an asteroid. Now, those are very small objects, keep in mind. Those are micrometer objects. So very, very small, but they can be 100% of the dark matter. Then the smallest stuff like Everest mass, black holes, even smaller. Whale mass. I live in a place where there's a lot of whales, so I have a personal attachment to whales. And then grain of salt black holes. So the Planck scale is a macroscopic scale. The Planck scale is the smallest, if you turn it into a length, it's the smallest length that it makes sense to talk about, but its mass, so it's unimaginably small, but its mass is about the mass of a grain of salt. Right, so that's the mass of the heaviest possible elementary particle, and it is the mass of the smallest possible black hole. So what I will not talk about in my colloquium today is where these black holes that are too light to be produced typically by astrophysical processes, so they don't come from the collapse of stars. So where else do they come from? And actually talking with Joe yesterday, we thought about the history of these primordial black holes. And for a long time, people claimed that there wasn't a clear mechanism or there wasn't evidence that it could abundantly produce these objects. But in fact, the field has evolved. And now the slate of possible candidates mechanisms that would form abundantly these non-stellar black holes is very rich. And again, I will not talk about this, even though I have worked quite a bit on them. And if you're interested in the JWST evidence for high redshift quasars, which of course would need some mechanism to form supermassive black holes at very high redshift, primordial black holes may do the trick. We have a recent paper on this that just got published. So if you're interested, please ask me. Also, let's keep in mind that it is unknown what the distribution in mass of these black holes is. In other words, how many of a given mass there are. And each one of these mechanisms would tell you what this mass function is, right? So you pick a formation scenario, you have a related distribution in mass of these black holes, which impacts the way in which you would search for these black holes, evidently. Very good. So, when Marco and I started our careers as dark matter physicists, the party line was that we should not think about primordial black holes because of plots like this. Okay, so this plot shows, as a function of the black hole mass in units of the solar mass on the x-axis, which fraction of the dark matter can be made up of primordial black holes, right? And the shaded areas are no bueno. You cannot be there, okay? And so as you can see, again, the party line was you shouldn't worry about this because at most, they're a small detail, right? They can never get to one. And so Marco and I looked somewhere else. However, this situation changed. And as I've emphasized, it is now clear that there is a window where black holes can be 100% of the dark matter. Also, there is substantial evidence that there's other windows where primordial black holes can be a very interesting fraction of the dark matter, more than 10% or so. So what changed? Well, some constraints, in fact, many constraints, changed because of something I will talk about in my talk, which is finite sized source effects. So you look for some lensing effect, but these lensing effects are affected by the source of the light that gets lensed being very large. And I'll elaborate on this later on. Then my smart colleagues at Harvard had done incorrect calculations of capture of black holes inside neutron stars. And here the argument goes that if you capture a black hole in a neutron star, the black hole grows because neutron stars are very dense. And eventually they eat the neutron stars. But we do see neutron stars where there's a lot of dark matter. And so based on this reasoning, there cannot be a lot of black holes. But this was wrong. It was wrong because they assumed some resonant capture mechanism that in fact was miscalculated. So these constraints went away. And again, this slave parameter space is now agreed upon to be viable for 100% of dark matter being black holes. So let me start this journey from the most massive possible black hole, which are about a stellar mass. So Marco and I, in our career, and Joe as well, have been thinking for a long time and continue to talk about whether there exists an unmistakable sort of background-free way to make sure that the signal comes from dark matter. Now, we're just talking about the galactic center axis. That's not one such signature, right? Because we don't really know whether those gamma rays from the center of the galaxy come from dark matter or from other things, cosmic rays or musical pulses. Now, when I started thinking about primordial black holes, I was very fascinated because, in fact, in this business, there is an absolutely clear, unmistakable signal of, yes, we're looking at least a component of the dark matter. And that is observing the merger of a very light black hole. In fact, so light that it cannot come from the collapse of stars. Okay, so if LIGO observes a subsolar mass event, then up to some exotic imposters, which may be there, which we may fight against, but this, is new physics faking other new physics. So to me, it's still interesting, right? We have, and please do ask me because I'm working on this as well. We do have an unmistakable signal of this primordial black holes being at least a fraction of the dark matter. Now, of course, the question is, do we have any hope of observing subsolar mass mergers? And so when you ask this question, what we did with a very smart former graduate student of mine, who's now a Price postdoc at MIT, was, okay, let's calculate the maximal possible rate at which these subsolar mass events can occur. And so this plane is the plane of, again, the fraction of PBH in the dark matter, ranging from 1% to 100%. And on the x-axis, you've got the fraction of these black holes, that would produce an event observable by LIGO. Okay, so of course, you can have mergers that are too far away or mergers of black holes that are too light to give a signal that would be measurable by LIGO. And what we find, optimizing numerically the mass function of black holes compatibly with all constraints, is that you can have over 10 events per year if you're lucky enough with the mass function. So that's interesting. In fact, it's so interesting that independent of our study, LIGO is actively searching for these events. And maybe it has found them. There's at least two rather compelling candidates for subsolar mass events in the LIGO data. One was found by a Spanish collaboration. It's called 170401. As you know, this is the year, this is the month, this is the day. So this event may be an April's 1st joke, maybe not. But of course, the issue is that the statement that this event is unmistakably subsolar mass is subject to a large uncertainty, right? It may actually not be a merger event at all. It may just be noise. In fact, if you ask LIGO, that's what they would tell you, right? This is just noise. There's no merger event there. There's another event from 2020 that also was claimed to be a subsolar mass merger. But again, the false event rate for this event is rather large. So this event as well is not convincing. But the point I'm trying to make here is we have the tools. We have the observational capabilities to see whether the dark matter is at least in part made of solar mass black holes. So stay tuned. Now, I said that this asteroid mass black holes is probably the most interesting range of masses for black holes to be 100% of the dark matter. I would talk about two things. First of all, the main way to detect these objects is through microlensing, and I'll explain what I mean by microlensing. And secondly, I will discuss how we can go after these objects, because microlensing is in fact very tricky to look for asteroid mass black holes. So this is what microlensing looks like. You have a star, and if the dark matter is made of black holes, every once in a while along your line of sight, you've got the transit of a black hole. Of course, this is an old story in extrasolar planets searches. but it works very well to look for black holes. And what happens is you enhance the brightness of stars for a certain amount of time that depends on the mass of the black hole, on the velocity of the black hole, on the relative distance between observer, source, and the transit black hole position. And so people did look for these microlensing events. And in fact, the best constraints are from a relatively short observation of this beautiful object, the Andromeda Galaxy, a nearby twin of the Milky Way. Now, I'm not an optical astronomer, but this camera, which is the Subaru Hyper Supreme camera built in Japan, is just an astonishing piece of equipment. In fact, so astonishing that it can monitor one by one millions of individual stars in Andromeda. So think about it. Andromeda is, hundreds of kiloparsecs away. And this telescope can make out individual stars and see if these individual stars get brighter over time. So that's to me stunning. In fact, because of my ignorance, I worked with a team of folks in Santa Cruz. This is my graduate student, now a postdoctoral appointee in Canada, Raja Gutakurta, who's a world expert on Andromeda and its stars, and Tessa Geltema, who besides being my wife, is also an expert on astrophysical matters. And what we did was to think about which stars of these millions of stars that I was mentioning are actually stars that Subaru can see. Now, when people first calculated these constraints, they assumed the simplest possible thing, which is Subaru was observing stellar objects of the size of the sun. Okay, but that was completely wrong because the sun is not very bright. And if you put the sun in Andromeda, actually Subaru is not able to make it out. Subaru is only able to make out much larger size stars than the sun. In fact, if you look at the distribution of stars that Subaru is sensitive to, the sun is about here. So the fraction of stars that have the size of the sun is tiny. All of the other stars are much, much bigger, factors of 10 larger than the sun in radius, okay? Up to factors of 17 or so. But that's a problem. It's a problem because if you have a large star, you have finite size source effects. So what are those? Well, to the ignorant mind of a theorist, the idea is the following. So again, you want to see the microlensing of a black hole, probably a much smaller black hole than this, the transits on your line of sight, and you get the amplification because light that would not get to you without a black hole does get to you. That makes sense. But now imagine that the star is very large, right? So what happens is, yes, you do get lensing, but that doesn't matter because this light would have gotten to you anyways, right? And so the amplitude of the microlensing is suppressed by the fact that you keep getting the light from this large object in the sky. Now, if you attach a slightly more intelligent terminology, what really matters is the relative size of the source in the sky, so the angular size of the source, compared to the so-called Einstein radius of the lens. Okay, so if the Einstein radius is much smaller than the source size, again, the magnification is suppressed. But you do have an upper limit on the lower limit on the magnification that you're sensitive to, right? If your magnification is just a tiny bit, Subaru is not going to tell you, hey, there's a larger brightness to that star. With the result that you lose sensitivity, obviously. In fact, you lose sensitivity quite rapidly. Notice that these are several orders of magnitude. And again, the old constraints were here. But if you take larger stars, they get weakened and you're sensitive to much more massive black holes that produce a much larger magnification. And so if you actually use this stellar population, which is key, right? Because you want to know how many stars of a given size you actually have in Andromeda, you put this together and you broaden up the parameter space that I was talking about quite significantly. Right, so if you're ever to use these microlensing constraints, please make sure to use ones that do take into account finite-sized source effects. So again, if you are taking home one message from this talk, primordial black holes in this mass range can be 100% of dark matter, and this range is actually larger than just killing previous constraints. Now, that's good. Mesmerizingly, we have seen several microlensing effects. So this is not just something that could happen, it did happen. Okay? And the theoretical prediction for the light curve of this microlensing event that we looked at before with this finite size source effect is in fact exactly what you observe. So these are observations of brightness of stars taken by Ogle. This is a Polish collaboration. And look at this data. It's beautiful. Right? Matches theory very, very well. Now, that's great. But are we really seeing black holes? Maybe not. Right? And we realized that, in fact, there is an unavoidable background, something that is called pretty floating planets. I like rogue planets better. So these rogue planets are planets that got ejected from planetary systems and have a mass typically at most the mass of the Earth or smaller masses. How does this happen? There's many, many ways in which you eject planets. In fact, if you have a system that comprises a star and a Jupiter-sized planet, you know, the life of smaller guys is not a happy one. You tend to spit out smaller guys very efficiently to just get an order of magnitude. You know, the time scale for ejection of an Earth-sized planet is in the mega years. So it's actually very short compared to the age of planetary systems. The good news is that NASA is launching in about a couple of years a telescope called the Nancy Grace Roman Space Telescope that is designed to precisely look for microlensing events. And so what this telescope will see is probably a lot of these rogue planets, these pretty floating planets, but maybe also primordial black holes, right? Sensitive to both and exactly identical. So the question, Joe, and something that I was mentioning yesterday, is can we tell one population from the other? Right? And of course, you can think of several ways to do that. For instance, you may imagine that Roman will look at places in the sky, directions in the sky where there's a lot more planets because there's a lot more stars, and places at high galactic latitude where there's fewer planets, but there's also a lot of dark matter. However, Roman is slated to mostly observe the galactic bulge, which is a place where there's both a lot of planets and a lot of dark matter. So what we did was to assume the worst case scenario, which is we are going to certainly have from Roman a bunch of events, and of these events, we will know one thing, which is the duration, how long the microlensing event lasts, okay? And what we did was to carry out extensive simulations with a code which is publicly available called lens called Pi. It's a very efficient code. If you want to use it, it's state of the art. And with this code, we simulated what happens to a population of primordial black holes in terms of histograms of event duration versus the number of observed objects, taking into account the performance of Roman. And as you can see, using an intelligent statistical test, you can be in a situation where there's clearly two bumps, okay, one from primordial black holes, presumably, and one from freely floating planets, whose mass distribution we sort of know, right? Because gravity has no scale, and so you should have a power law of planets that get ejected, right? You eject more easily lighter things, but there shouldn't be any feature, right? You sort of have a continuum in mass. Primordial black holes, on the other hand, tend to be clustered around one specific mass, which is what we assume here. And so if that's the case, you may be lucky or unlucky. You may stack the two distributions on top of one another, or you may be able, by using smart statistics, to tell one from the other. Now, that's good. It's good because we calculate that the sensitivity of Roman will, for instance, tell us whether the Ogle events are primordial black holes or free floating planets, very conclusively, even if the free floating planet abundance is not that big. By the way, I had no idea, But these free-floating planets, there's a lot of them, right? So the floor of the abundance of free-floating planets is there's as many free-floating planets as bound planets. So we know that at least that is the case. But most likely, there's 10 to 100 times more free-floating planets in the galaxy. These very sad worlds, very cold worlds, rather uninteresting worlds, than stuff that is bound to stars. This is like, wow. It's really interesting. They think about dark matter, but there's a lot of other interesting stuff out there to learn. Cool. So that's good. That's good because we have a way to discriminate potentially free-floating planets, our background, from primordial black holes. But it's also bad because the window I'm interested in is here, starts here and goes to the left. But Roman will only probe stuff that is much heavier. And the reason is that Roman has a cadence with which they observe stars, and light objects have microlensing events that last very little. They last very, very little. In fact, so little that Roman will not even see this brightness, the microlensing event. So this begs the question, how are we going to go after these asteroid mass black holes? So one possible way, I was also discussing with Chloe yesterday, is these black holes would form pairs. Pairs would merge, and the merger of black holes, as you well know, produces gravitational waves. So there should be a background of gravitational waves. Also, production mechanisms may source directly gravitational waves. And I don't have time to talk about it, but isocurvature perturbations are a very natural way to produce black holes, and they also inevitably produce gravitational waves. Of course, you may think about higher frequency observations. These would indeed probe lighter masses, but those are tricky because you need to monitor millions of sources, and we don't know how to monitor millions of X-ray or gamma ray sources, right, effectively. So that's a problem as well. But maybe we have a chance to directly see individual mergers of these light primordial black holes. And in fact, I talked about this yesterday in my seminar, and the key idea is that gravitational waves couple to electromagnetic fields in exactly the same way that axions couple, all right? And so what you can do is you can repurpose axion search experiments like ADMX, resonant cavities, to instead of looking for that dark matter candidate, you can look at transient merger events that come from gravitational waves. Again, this is something that I'm very interested in, especially because we actually convinced ADMX collaboration to look for these transient events. They usually don't look for transients at all because axions are not transient. And so stay tuned because there may be good news about this. Good. So black holes explode. Hawking called the process of evaporation at the end of a black hole's life, black hole explosion. So let me give you a little bit of background on this. If you build a field theory in the background of a Schwarzschild metric, then that field theory lives in a thermal background that depends on the inverse of the mass of the black hole. So the temperature of that background that you inevitably observe, again, if you just put your simple quantum field theory in the background of Schwarzschild, you observe this phenomenon, right? But that's interesting because it means that black holes are hot, right? They have a temperature. The smaller they are, the larger the temperature. But we know what happens when a body is hot because in kindergarten, we all studied the Stefan-Boltzmann law. And the Stefan-Boltzmann law tells us that a body at temperature T radiates proportionally to its area and with the fourth power of temperature. Okay? But the area of a black hole is the square, goes like the square of its radius. But the radius of a black hole is proportional to mass. So area goes like mass squared. Temperature goes like 1 over mass. So you've got mass squared over mass to the 4. And so you get that the evolution of the mass of a black hole, the evolution of mass of a black hole is inversely proportional to the square of its mass. So even I can actually integrate this differential equation. And you see that this differential equation, right, you just move dt on this side, you move m squared down here, you take the integral, and you realize that black hole lifetimes go with the cube of the black hole mass. With the cube of the black hole mass. So if you have a very massive black hole, say a stellar mass black hole, that guy's gonna live for a very, very long time, right? In fact, it doesn't lose any mass. It's so massive that it eats up more stuff than it spits out. But if the black hole is small, in fact, if the black hole is on the order of 10 to the 10 grams, what I'm gonna call whale black holes, these guys evaporate in a matter of seconds, in a few minutes. Okay, they just explode. And the explosion is a runaway process because the emission goes like 1 over the mass squared. So as the mass gets very small, the stuff you emit is very large. So that's cool. And in particular, you may realize from this formula that the age of the universe, which funnily enough is pi times 10 to the 17 seconds. If you take home another thing from this talk, is the age of the universe is pi times 10 to the 17, very closely. Anyways, if you put pi times 10 to the 17 in this equation, you get that a black hole of mass 5 times 10 to the 14 grams lasts the age of the universe. Okay? So those black holes cannot be the dark matter because they're essentially disappearing right now if they form very early on. But this is very cool because another thing that black holes do is they're perfect standard candles. The way in which they evaporate is exactly identical for every black hole. So this universal luminosity, what I'm plotting here as a function of time to expiration, I plot the luminosity of the black hole that you get out. So the number in this case of photons that you get out of a black hole. And it's rather large. This is in units of 10 to the 30 per second photons. So what this really looks like in the sky is essentially a backwards GRB. Right. GRB, usually it's a big explosion and then you have a tail, like an afterglow. Here it's the opposite. You get first the afterglow and then the explosion. And then nothing right after. Okay. So that's interesting, especially because there's one way in which you could modify this light curve. Black holes are very democratic. You know, they're very left-wing, and they evaporate into anything there is to evaporate in. And so if you add new degrees of freedom, and these degrees of freedom don't need to couple at all with us, then you speed up black hole evaporation. So in fact, the light curve is a fantastic messenger of secluded dark sectors. So even if a dark sector exists, but doesn't talk to us at all, it does affect the luminosity curve of a black hole. So that's rather interesting. And in fact, I have a paper out with a fantastic undergraduate student where we use this to probe the size of dark sectors if we detect a black hole explosion. Again, please do ask me about this. I don't have time to go into details. But what I do want to talk about is, can we observe black hole explosions? Or have black hole explosions been observed? Okay, so I will discuss in the next 5 minutes a plot where I show as a function of the mass of the evaporating black hole. Now, this object may be evaporating right now. It may not be fully exploding right now. It may just be in part of the runaway process of exploding as a function of where this object that is exploding is, right? Because that's obviously relevant as to whether or not we can observe it. Now, please notice that, as I said, the lighter the black hole is the mass at detection, the quicker the explosion is. So in fact, for black holes that weigh 1,000 kilograms a ton, this is a very rapid process, but it becomes the age of the universe also rather rapidly, right? 10 to the 14 because of this n cube dependence that I demonstrated to you just a couple of slides ago. So the other key thing, if I want to detect these objects, is understanding what to use to look for them. And what to use depends on the temperature of the black hole, because remember, black holes are just hot bodies at a given temperature. So they emit a black body spectrum of light that peaks at whatever this temperature is. And so if you're interested in observing this mass black hole, you'd better use a telescope that is sensitive to MEV photons. But if you're interested in looking at lighter black holes, then you can call up Sylvia and ask her, okay, let's use Fermi data to look for this thing. All right. So here is the sensitivity of a variety of telescopes to these explosions. So I have CTA, the Cherenkov telescope array. I've got Veritas, which is also a Cherenkov array, older generation. LASSO, a Chinese experiment that merges both high energy, very high energy cosmic ray detectors with a Cherenkov telescope system. HAWK, water Cherenkov telescope. The LAT, the Fermi Large Area Telescope. The gamma ray burst monitor on board Fermi. And each one of these telescopes does better or worse at different temperatures, so different masses of the black hole. So if you're south of these curves, you have a chance at detecting them. You know, in that area, the signal to noise should be greater than 1. Again, I'm a theorist, so this is quite rough. And there's very good reasons for the shape of these curves. You know, if you're here, you have very short bursts, so you don't have a lot of photons to capture. This is limited by the fact that your observing time is at most the life of a graduate student, so it's limited. And as you go to longer events, eventually, you know, you just run out of the energy range that you're sensitive. Now, there's one thing that I'd like you to notice. These are very small distances. So we're talking about fractions of a parsec. In fact, this point here is 1 astronomical unit. So I'm talking about stuff that happens very close to us. Okay, and that's actually okay, because if these are the dark matter, there's a lot of them. In particular, there's a lot of them in the solar system. So we just have to be lucky that some of these guys are exploding right now. Right? However, if these guys are so close, and if the explosion lasts some sizable amount of time, you're going to see them move in the sky. Right? They're going to have a proper motion. Because what are the chances that as they explode, they're exactly along our line of sight, very small, right? So you should observe a proper motion. Does that make sense? All right. Good. So let's take this fact into account, and let's do the exercise of observing the transient sources that the LAT has observed. And that's what you get. You know, there's a few sources that evidently are increasing in luminosity. Well, I don't know if it's really evident. Look at the error bars. Is this increasing? Maybe not. You know, the best fit is increasing. So let's go ahead and take these sources seriously, and maybe also look at the spectral index of the photon emission at some pivot point. Again, uncertainties are huge. And let's plot them over here. These are all of the transient sources whose luminosity is increasing. And you've got a couple of clusters of sources, some that are very slowly evaporating, some that are evaporating more quickly. Of course, they all have to be within the LAT sensitivity, which they are. But here's the problem. The problem is that none of these sources moves in the sky because they're all extragalactic, of course. But, you know, if LAT detected a source like this that was increasing with luminosity and that did move in the sky, bingo. You know, this would most likely be a very nearby event. And, you know, it could very well be. We have, again, these are perfect standard candles. We know exactly what we should observe. So the chase is on. The chase is on. Another thing that you may do is to look at whether we see any reverse gamma ray bursts. And the sad news is that we don't. Okay, I'm trying to find a clock. Is there a... Okay, so I'm sort of running. Okay, I have until 11:30.
I have until 12 in principle. So
Oh,
I have about 10 more minutes.
Oh, okay, very good. So I'll move a little bit faster. Short answer is we don't see any backwards gamma ray bursts, but we may. In fact, I think the best way to look for these things is to use the so-called interplanetary gamma ray burst monitors. And the reason is that these things would actually observe different times of arrival if the source is very close, right? If there is an explosion in the solar system, you would see that explosion at different times with different telescopes around the Earth. So we're actually working with the team that manages the IGRB, which is one person. The person is Russian, and so he's busy with other matters these days. But you know, these are out there and they have data. Now I won't talk about the particle physics aspects of evaporation. Let me just say that they're very interesting because of the fact that the relevant temperatures are close to the QCD confinement phase transition. And there's ideas to build MEV telescopes. Again, ask me if you're interested. Joe, I was mentioning that you know, using our code is important. How do you see it's important? Well, in the past, people used the geometric optics approximation. This is the right curve, and that is wrong. People used also this curve. You know, it's off by several orders of magnitude. So you probably want to use this thing that's called HASMA. If you like Pokemon, you recognize where HASMA comes from. It's the radioactive Pokemon. Anyways, this is all implemented. It's a beautiful piece of software by two French researchers, RB and Offinger. One of them, unfortunately, went to the industry, but our code is implemented in this code, and it's a beautiful piece of code to study evaporation. I won't talk about this, which is where constraints are in developing black holes. Because I want to now talk about lighter black holes that are gone, that are long gone, that exploded in the early universe. So what about them? Well, they can be very interesting because explosions of black holes, again, are very democratic. They produce anything, including they could produce dark matter. They could also produce a baryon asymmetry. Okay? So the explosion of black holes in the early universe, and these black holes are not the dark matter, but they may have produced the dark matter. Also, if you work a little bit on the GR side of things, you may convince yourself that if the action of general relativity contains a coupling of the Kreshman-Scatter's time derivative with the B minus L current, and again, if you're into these things, I can give you many details, then the evaporation of black holes directly sources a baryon asymmetry. So the fact that space-time is evolving induces a source of a matter-antimatter asymmetry, which is very interesting. You may want to use a simplest scalar here, maybe the Ricci scalar, but that doesn't work because the Ricci scalar is a constant in evaporating black hole. So you gotta use this gnarlier object of pressure. Also, if black holes have exploded in the early universe, everything that they produce in terms of standard model particles has thermalized in the early universe plasma, so it's gone, you cannot observe it. But there's one exception, graviton. Right? Black holes produce gravitons from evaporation, they produce gravitational waves, therefore, and those are observed. Okay? They're produced very early on, so even if they're very high frequency initially, they get redshifted down to frequencies that maybe we can observe. And again, if you're interested, we have a few papers on this, and I'm very interested on that. Let me get to my last part of the spectrum of black holes that I want to talk about, grain of salt black holes. So this is, again, something that we were talking about yesterday with Maria and Joe. If evaporation stops at some point, so if you don't completely get rid of a black hole, you're left with a radic. The most natural radic size is Planck mass radics. And one thing that could stop evaporation is that the black hole becomes extremal. What does that mean? If the black hole is charged, or if it's got some angular momentum, then its horizon size shrinks. Okay? And since the horizon size is related to the temperature of the black hole, if the horizon disappears because of charge, then evaporation stops. Because an object at t equals 0 doesn't evaporate anymore. And so if you charge black holes, they become extremal before disappearing. They become stable. They're around today. And they can be the dark matter. Now, it's interesting because we sort of know, since evaporation is a random process, that you probably don't evaporate identically in, say, positrons and electrons. And if there is a difference in the number of electrons and positrons it evaporates into, there is a net charge that the black hole inherits, right? And so black holes are charged if they're Planck relics, and they have a charge distribution that is approximately Gaussian with this width in units of the fundamental charge of electrons. So do we have any hope of detecting these Planck relics? And this is the last plot I'm going to show you today. And yes, we have hope. Because even if these objects are very massive, if they carry electric charge, we can repurpose dark matter detection devices to look for the tracks left by these massive charged particles plowing through the detectors and ionizing stuff, producing all the things that, for instance, xenon 1 looks for. Neutrino telescopes also would see a signal, as this stuff produces a bunch of sharing of light and other things that these detectors are sensitive to. But the best way you have to detect charged grain of salt mass black holes is paleodetectors. Ancient crystals that are very regular, have lived underground for billions of years, undisturbed by cosmic rays. And if you've got a track inside these crystals, which disrupts the crystals, then you may have a direct access to the passage of a charged mini black hole at very ancient times. So in fact, you're sensitive to relics that can be as heavy as 10 times the mass of the Planck scale, with, for instance, ancient mica, even if this is just 1,000th the dark matter. Okay, so that's pretty compelling. Good. So let's look back at what we talked about today. I talked about stellar mass black holes. These objects are detectable because if you see a subsolar mass event with LIGO, you may strike jackpot. You may actually have an unmistakable signal that the dark matter is at least in part made of stellar mass black holes. If black holes are lighter, in fact, asteroid mass, they can be 100% of the dark matter. Unfortunately, searching for these objects is tricky. Microlensing is very tricky. Typically, it's not sensitive to small enough masses, but there's other ideas out there that could work. Unfortunately, we have backgrounds there. There's rogue planets that get in the way. So you got to work a little bit harder. It's not just black holes that make habit that mass range. If black holes are exploding right now, we have a chance at detecting them. They look sort of like reverse GRBs. Good news is that they have a universal light curve. This is a powerful window into dark sectors, again, because the light curve changes if you add new particles to evaporate into. And the best constraints we have, which I didn't talk about, are diffuse gamma rays. If black holes have completely disappeared, they may have given us a gift. And the gift could be the production of dark matter, the production of baryonic symmetry, or gravitational waves. All these things may have been produced by the early evaporation of light black holes. And finally, if evaporation stops, then the leftovers of evaporation are slated to carry some electric charge. And as such, they are detectable, probably best detectable with paleodetectors. I will stop here. Thank you.
Thank you, Stefano. Very inspiring. So, questions, please.
Thank you for the really nice talk. I have a very basic question. How can black hole evaporation create baryonic symmetry?
Oh, very good. So there's a couple of ways. One that I talked about is if you have the coupling of the Kretschmann scalar, which is an object that is very interesting because it's both CP violating and could be coupled to the B minus cell current, so it could violate baryon number. And so what happens is evaporation sees this Kretschmann scalar coupling. And so as the black hole evaporates, it emits particles asymmetrically into baryons and antibaryons, or positrons and anti.
So if I recall, if I remember correctly, you need three kind of Sakharov conditions.
Yes. So the out of equilibrium, very good. And the out of equilibrium condition comes from the fact that the evaporation process and the change with time of the black hole is not in thermal equilibrium, right? You just turn the temperature down, not because you're in thermal contact with the bath. So you have violation of CP, violation of B, and an out of equilibrium process. Another possibility is that the black holes source heavy right-handed neutrinos, and then you can do baryogenesis via those guys, via leptogenesis. So that's another possibility. So there's a few mechanisms.
Yes.
In the case of stellar mass black holes, which will be seen by LIGO Virgo with gravitational waves, the problem is that you have to figure out that these are really black holes and not neutron stars or some exotic object like boson star or something else. And for this, you have to measure the merger itself. And for these masses, the merger occurs at very high frequency. And so the sun detectors are not sensitive enough to measure the merger, which will distinguish between black holes or neutron stars.
Absolutely, that's a very good point. The good news is that we know neutron stars cannot be arbitrarily light in the standard model. And so if you're lucky enough that the merger is close enough that you could actually see it in spiral when the frequency is not too high, then you may actually be able to detect the high frequency part of the low frequency part of the merger and estimate the mass conclusively enough to be convincingly below the neutron star. I absolutely agree with you that there's exotic objects that have the compactness and the mass to fake this signal. But the good news is that that's new physics anyways. And the second thing that I'm working on is that the log numbers of these objects is not necessarily zero. If you have a black hole, the log numbers are zero. And so if you're lucky enough that you get some information on the log numbers of the merging black holes, then you can actually discriminate between, say, a boson star and an actual compactness equals 1/2 object. So I agree with you, it's not an easy job, but LIGO has a lot of smart people, maybe including you, looking at this, and so I keep my fingers crossed.
Yes, David.
You mentioned isocurvature entropy fluctuations to produce primordial black holes, but isn't this channel excluded given the Planck constraints, which is 5% of adiabatic fluctuations?
Good. Very good question. So the answer is no, because Planck constrains isocurvature perturbations and the ensuing gravitational waves at very low frequencies and in narrow range. So generally, those are not interesting for the formation of black holes because the black holes will be very, 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 very small. Okay, so you do get constraints from isocurvature perturbations limits from Planck, but usually the actually interesting gravitational wave frequencies are much higher than where Planck is sensitive to. Yes.
Yes, I have a rather naive question. You said that the evaporation of the black hole is universal, but I saw something like 2 years ago about there is a stabilization mechanism via the memory burden quantum information things, and does it change the picture or?
Yeah. So there's been quite a bit of chatter about memory burden effects. I've written a paper on this, but I'm really unconvinced about the possibility that these sort of high-level arguments apply in practice. However, you pose a very and not at all naive question. And to be honest with you, the light curve is not exactly universal because, as you know, the so-called gray body factors of a black hole that has no charge and no spin are different from the gray body factors of an object that does have spin and charge. But those are relatively small corrections. The general idea, if a black hole has spin, it likes to spit out higher spin particles, and so the evaporation is slightly different. But that's a mild correction.
So you have no effects from back reaction after the half evaporation that can change anything?
No, back reaction effects, something I thought quite a bit about. They don't affect really evaporation at all. So the light curve is unaffected by that completely. Yes.
Yeah, I'm going to ask an even more naive question because as an observer, of course, I spent my whole life imagining that dark matter is smoothly distributed on large scales. And I'm quite involved in Euclid, for instance. So what effect, if you're telling me dark matter is in point-like sources, which are lesser than a smoothly distributed dark matter, what effect does that have, for instance, on gravitational lensing statistics?
Excellent question. And in fact, not naive at all. So there's an easy way to think about this. So as you know, the matter power spectrum is affected if you have point-like objects at small scales, because essentially you are seeing the fact that you have individual gravitational potential wells. And so there are length scales in a matter power spectrum where you see that. And people call it, in honor of this great country, the Poisson effect, right? So you have individual objects, and the Poisson effect in the matter power spectrum is a very simple thing to recognize because it scales essentially proportionally to k, the wave number. And so what you would have in your transfer function in the matter power spectrum at small scales that of course depend on the mass of the black hole, is an increase of the matter power spectrum at small scales. Okay, so it's kind of going in the opposite direction as, say, small scale suppression that comes from, say, warm dark matter, self-interacting dark matter. So at small scale, you have this proportional to k effect in the matter power spectrum that would be very recognizable. Now that, in turn, depends on where this sets in. If it sets in at extremely small scales, then you don't have any gravitational lensing effect that is measurable. But you may be lucky. If there is a subpopulation, maybe it's a small effect, but it's a large enough scale that you guys may be able to measure it. So we're actually working on this. And believe it or not, there's an even more interesting possibility. If these black holes are charged, under, say, a dark charge, not electromagnetism, then they attract one another. And so they are self-interacting. And so you have this dual effect of the suppression of small scale because of self-interacting effects, and then the enhancement at even smaller scales, or a combination of the two. So the matter power spectrum is a very interesting tool to look for discrete dark matter candidates. And of course, I talked about black holes, but if you have compact objects, Witten talked about strangelets and composite dark sector objects. So you may have many discrete dark matter candidates that essentially induce the same Poisson effect at small scales.
I'll just add a quick piece of information is that it's recently been approved to do a micro-lensing survey of the bulge with Euclid. And so Jean-Philippe Beaulieu at the EIP is involved in that. And so that should provide a nice, very long baseline between Roman and Euclid. The observations will take place this year.
Beautiful news. Thank you for sharing.
Yes, black hole evaporation is of course fascinating, but these black holes, which some of them might even reside in the solar system, there's plenty of matter around, so there should be accretion of that. So that generates some kind of diffuse background, X-ray background, something like that, which at some stage could be detectable, perhaps?
Excellent question. The answer is yes, but there's this notion that black holes are very dangerous because you may fall on them very hard. Okay, so these black holes are tiny, and the accretion rate essentially depends on the cross-section because it's a gravitational process. And so the cross-section scales with area. So small black holes accrete very inefficiently. However, larger black holes, in fact, accrete quite efficiently. And so there are very strong constraints. If I have the patience of clicking 1,000 times, I get back to a slide where I was showing constraints at very high masses. And so there, the idea is that accretion is most efficient when you have high densities. And so in fact, instead of the late universe, a good place to look for this is the early universe around CME recombination. And the CME recombination, I got sick of clicking, so I'm just going to use a better method. And a CME recombination what you have is that you deform the spectrum, the black body spectrum of the CMB. You essentially give a chemical potential. You change the mu of the distribution. And so this comes in play here. Okay, and as you can see, these are 1,000 solar mass black holes. These are accrete efficiently, and you can set very powerful constraints here because you would distort the CMB spectrum. You would essentially, produce electrons that kick the CMB photons, distorting a CMB. But at late times, accretion for small black holes is very inefficient, and so the constraints are rather weak.
So let me take the chairman's prerogative, ask you a question.
Yes.
You mentioned the cadence is a real issue for these very, very low mass things because they explode so rapidly. But maybe there is a trick one can use because all of their emission goes into a diffuse background, which maybe you can't see that far away, but it could sample volumes of megaparsecs or more. That's potentially interesting for a very high energy signal.
Yes, that is absolutely very interesting. Joe, the problem is that we don't know how many black holes are evaporating when. You can make assumptions. And so, you can say maybe you have a population of black holes in your universe that have evaporated. Maybe they are evaporating in the late universe. And so, the products of evaporation and of explosion are detectable. But in fact, you get much better constraints from black holes that have not exploded yet, but are in the process of spitting out stuff slowly but surely. And so the diffuse backgrounds that you get from these slower evaporating, more massive black holes are in fact more powerful to set constraints than the emission from lighter black holes that are closer to the final stage of evaporation. So it's kind of like a balance of the two, and what wins is the heavier black holes.
So thank you. So if there are no more urgent questions, let's thank our speakers.
No,